Hi, welcome back to Maths Plus with Armien. In this video, we're going to look at differential calculus. This is part 1 of 5 parts. In the introduction to differential calculus, we're going to look at limits, first principles, and differentiation rules. Firstly, we're going to look at the concept of a limit. Then we're going to look at the concept of a derivative of a function. Then we're going to determine derivatives using a technique which is known as using first principles. Then we're going to use what we've seen from first principles to determine some differentiation rules, and then we're going to apply these rules. We're also going to briefly tell you why you need to study calculus, and then, as usual, there'll be an exercise worksheet for you to practice these concepts. Before we start, let's look at some mathematical symbols that we'll be using. Which one is this? That's right, equality. Example, x is equal to 2. X is exactly equal to 2. For example, x cubed is equal to 8. We find the value of x. That's right, x is exactly equal to 2. And this one. This is the one we use when we round off calculations. And this is known as the approximation symbol. For example, x is approximately 2. Right? Not exactly, approximately. For example, if I have x equal to the 5th root of 35, go to the calculator, it gives you 2,03, but we can say it's approximately 2. Right. This one, this is a new one that we're going to use. This one we say is approaches or tends to. X approaches 2. What do we mean by approaching 2? In other words, it's a number close to 2. Can you give me a number close to 2? 3. Yes, 3 is close, but not. When you say close, you want it very close. So something very close, that's right, 2,5. Closer, 2,1. Closer, 2,01. Even closer, 2,0001. Right? Get the idea? But you can also go a little bit smaller than 2, but still close to 2. So, give me an example. 1,9. 1,99, 1,999. The more 9s I take, the closer I get to 2. And this is the one that we'll be using a lot in this lesson here. That symbol. X approaches 2. Let's start with some everyday use of the term limit. Okay. Speed limit. You know what that means? There's a speed limit of 60. What does it mean? You are required to drive at 60 kilometers, but nobody actually drives exactly at 6. You can go a little bit over, a little bit less. If you travel at 80 kilometers, then we say you've exceeded the limit. 60,5 or 61, you're very close to the actual speed limit. You have a spending limit. Your mom gives you some money and said you can spend, you have a limit of 100 rand. So if you spend out 101, not a problem, you're close to your limit. But if you're going to spend out 200, then you've exceeded your limit. Right? You can go a little bit more or a little bit less, and you're within that limit. Age limit. You might say there's an age limit of 60, so somebody comes and he says he's 59, it's very close. Right? Or 61, very close. But if you come at 80, no, that's not the age limit. You can be a little bit flexible there. Very close to the number. A little bit more or a little bit less. Time limit. You're given a time limit of doing something in 5 minutes. You're expected to do it in 5 minutes. If you can do it in 4,9, good for you. If you take 5,1, take a little bit longer. It's not, but you can't go and take 10 minutes, right? And you exceeded the time limit. So we want to get close to that limit. Let's look at some mathematical examples of the limit concept. Let us investigate the area of some regular polygons. Do you still remember what's a regular polygon? That's right. It's a polygon where all the sides are equal as well as all the interior angles are equal. For example, what's the smallest one? That's right, a triangle. What type of triangle? Equilateral. Let's look at this one. So there we have an equilateral triangle, the polygon consisting of 3 sides. Now, if we look at that polygon, we now notice, compare the polygon with the circle. See, the triangle is inscribed in the circle. And we can see the difference between the two, right? The circle is much bigger than the triangle. So the triangle's area is less than the area of the circle. But if we take a polygon in the same circle, but we increase the number of sides. So from n equal to 3, let's try n equal to 4. What type of polygon is that? What's the name of the specific polygon? Square. And you can see, you see the difference there. That black is the difference between the circle and the triangle, or between the circle and the polygon. And if I take 5 sides, this we call a pentagon. And you see the difference becomes smaller. In other words, the polygon gets closer to the area of the circle. That's a pentagon. One with 6, that's a hexagon. Gets closer even. And the one with 7, that's a heptagon. Even gets closer. And one with 8, what we refer to that one? Or octagon, right? And then we take one with 10, that's a decagon. And then we can go on, we can have 12 and 14, there's 14, gets closer. And the more sides we take, the closer it gets to the circle. So, if the area of a polygon, the area of a regular polygon is equal to the area of a circumscribed circle, if the number of sides of the polygon approaches infinity. So the more sides I have, the closer it gets to the circle. Well, that's a lot of words. In mathematics, we'll try to write as little as possible. So we can say the limit value of the area of the polygon as n approaches infinity, approaches the area of the circle. That's still a lot. Limit value, we can just write down lim, lim, and below it we write down n approaches infinity. So the limit as n approaches infinity of the area of the polygon is equal to the area of the circumscribed circle. Let's take another example. Let us investigate the sum of the following series. We take a geometric series, half plus a quarter plus an eighth plus 1 over 16 plus 1 over 32, etc. Right? Let's look at it geometrically. Let's say I take a square. So half would be, that's half of the square. And then I take half of what is left, that's a quarter. Then I take half of what is left, that's an eighth. And then I take half of what is left, that's 1 over 16. And I can continue, that's half, 1 over 32. And then again, 1 over 64. Now it becomes a little bit too small to write in the value, 1 over 128. And then 1 over 256, etc. And I can continue, and you can see as I go, it gets closer and closer to filling the whole square. So the sum of that, as I make the n as large as possible, it gets closer and closer to 1. So we would say the limit there of that series is equal to. Let's take some examples. Let's look at this fx equal to 2x minus 2 over x minus 1, where x is equal to 1. Let's investigate where x is equal to 1. And you see that's what we get when we substitute. We calculate the numerator and the denominator. They're both 0. That tells me it's undefined. So f1 does not exist. Let's look at it algebraically. 2x minus 2 over x minus 1. We simplify that by factorization. And cancelling out, we end up with a 2. But is fx equal to 2? Yes, but only if x is not equal to 1. Because if x is equal to 1, it doesn't exist. Let's look at it analytically. Now we want to see where x approaches 1. Those values you can see approach 1. You can also approach it on the right side, and we can also approach it on the left side of 1. Now let's go to the calculator, and we just try to work out the output values there. 1,01, substitute it in there. The same there, 0,99. We do all of them. I give you a chance. Shouldn't take you 1 minute to complete all of them. Let's see. So after calculating, we see the values. They are 2, 2, 2, 2, and even for the ones on the other side, they're all 2. Okay. Let's look at it graphically. Fx equal to 2 is actually a horizontal line, but there's one place where it's not defined. For x equal to 1, it's not defined. See, that's why we've got an open spot there. So when x equal to 1, it's not defined, but to the right side of 1, it approaches 2, and to the left side of 1, it actually is 2 as well. So the limit value of this function defined by fx as x approaches 1 is 2. You can write that in a much shorter way. The limit as x approach 1 of fx is equal to 2. Let's look at the second example. Gx is equal to x squared plus 2x divided by x, where x is equal to 0. Let's determine g0. Again, there we see the denominator is 0, which implies that g0 is undefined. Let's look at it algebraically. X squared plus 2x, that can be factorized. We can cancel out the x's, and we end up with a simplified expression, x plus 2. Is gx equal to x plus 2? Yes, but with the restriction, x should not be equal to 0. Let's look at it analytically. Where x is equal to 0, so 0 is undefined. So let's look on the right side of 0 and the left side of 0. There's some values on the right getting closer to 0. There's some values on the left getting closer to 0. The one is on the right and these are on the left. Let's determine the output values using the calculator. Let's do that. We see they all come out to 2, and we put that in and they all come out to 2. Let's look at it graphically. Gx equal to x plus 2 is a straight line, but at x equal to 0, see there's a hole in there, there's a gap in there. It's undefined by x equal to 0. So the limit value of gx as x approaches 0, the right side and the left side, will be 2. See, it gets closer to 2, which we can write in a simplified form as lim as x approaches 0 of gx is equal to 2. Let's take a third example. What about h2? Let's calculate that. Again, there we see we end up 0 in the denominator. Therefore, it is undefined. Let's look at it algebraically. Let's simplify that by factorizing. And then there we see the two factors are cancelling out. And I end up with x squared. Is hx equal to x squared? Only if, that's right, only if x is not a 2. Because if that was a 2, it would not be valid. Let's look at it analytically. A value greater than 2. Those are some values approaching 2, right? And this one gets closer to 2. Let's take this one. This gets closer to 2. So the more zeros I have, the closer to 2. The more 9s, the closer to 2. Let's compute that. Go to the calculator. I give you some time. It's 2,01. Complete this table. And if we look at that, those are the values that we get. And if we complete that table, those are the values that we get. What do we notice there? As we get closer to 2, the value gets, that's right, it gets closer to 4. As it gets closer to 2, it also seems to get closer to 4. Let's look at it graphically. X squared is a quadratic, but this is a quadratic where it's not defined by x equal to 2. It's undefined there. That's why we have an opening there. So we can see here that the limit of hx as x approaches 2 is actually 4, which we can write in that form there. Now let's evaluate limits, but we're not going to do it using the calculator or not doing it graphically. We're going to try to do it algebraically. And we're going to use the following. If fx is a polynomial, then the limit value is equal to the function value. In other words, if you're busy with polynomials, you can just, instead of working out limit value is the same as the function value. So here we have three polynomials, a 10, 4x minus 1, x squared minus 2x plus 4. So if this is a polynomial, I can do substitution, but limit of 10, it's a constant, so that just remains the constant 10. If I take 4x minus 1, the limit of this, because this is a polynomial, I can just substitute. So that gives me negative 9. This again is a polynomial, so I can just do a direct substitution there. Let's look at examples where we do not have. Let's look at some rational expressions there. In this case, we have a denominator, and the denominator is the one we must always be careful of. If it's non-zero, we can just calculate the function 0. But if the denominator is 0, we first have to simplify the expression. Let's look at this rational expression here. If I look at this, let's look at the denominator. 3 plus 1, no problem. So I can just substitute. And that gives me 9 over 4. Negative 2 plus 2, there is a bit problematic. So what do we have to do first? Let's try to simplify it first. So we factorize and we simplify. Now I end up with a polynomial. Then I can just substitute. Let's take this one. Again here, if I have a 0, that's a problem. So I rather simplify first. If I simplify that, I end up with x minus 1, which is now a polynomial. Because I have a polynomial, the limit of the polynomial is the same as the function value. Now, next we're going to look at the concept of the derivative of a function and show you what we mean by derivative. Previously in our linear function, we look at the gradient of a straight line. But we want to look at what's the gradient of curves. So to start off, let's look at, first of all, the gradient of a secant of a curve. What is a secant? That's right, it's a line that cuts a circle at 2 points. So we're going to look at the gradient of a secant AB. So there we have a function, and you can see this particular function here. There's the function, and we have 2 points. There's a point A and a point B, and we are joining that, and there we have a secant, right? Secant AB. Now we have the x coordinate of A, which is x, and the corresponding y coordinate is fx. Then we have another point, point B. Normally we would say this is x1 and x2, but this is more than x, so we refer to this as x plus h. So x plus h is the x coordinate of B, and we have the corresponding fx plus h. Okay. So there we have point A, which is A and fx, and point B, which is xh and fx plus h. Okay. So this is going to be xa, and this is the xb coordinate. This is the yb, and this is the ya coordinate. Gradient. What is a gradient? What's the definition? That's right, the change in the y over the change in the x. In analytical geometry, we had that as yb minus ya over xb minus xa. yb minus ya over xb minus xa. Okay. But if we now use yb, you can see what is yb? fx plus h, that's the yb. And the ya is fx. The xb is the x plus h, so there's the xb. And the xa is x, so I have that. And this x and that x will give you a 0. X subtract x is 0. And we end up with that quotient there. Now this fraction, fx plus h minus fx over h, which is actually the gradient of the secant. This one here, there's a mathematician after whom this particular fraction is known, and that is, any one of you know, very famous physicist or mathematician? That's right, Newton's quotient. Right? Now this also, so the gradient of AB is also known as Newton's quotient if it's written in this form. And then you have the average rate of change. This is also the average rate of change. Now we want to proceed, because we want to find the gradient of a curve at a specific point. We're going to look at the gradient of a tangent of a curve. Let's see how we can get a tangent. What did we say was this again? That is a secant. Now you see there I have it A to B, but let's say instead of having the point B there, I could have another point down here, right? So I can have a secant like that. So in other words, there's x and x plus h. So maybe if that h was, let's say, comma 9, so, and this was 2, so that will be 2 comma 9. And this one will be less, so that maybe it could be 2 comma 8, and or x plus comma 8. And this one here could maybe be x plus comma 6, and I can get closer and closer to the a. Can you see there's the b? If I have instead of the point there, I could have another point there and another one. It gets closer and closer to b. And this h becomes smaller and smaller until eventually it becomes so small. And the smallest it can become is, that's right, if it approaches 0. And if I keep on doing that, there we get a line like that. And what do we refer to that line? Let's look at it. That's it. This is a tangent, right? A tangent is when it touches only at point A. So how did we develop that? We took Newton's quotient. But what was the denominator of Newton's quotient? That's right, h. So if we let the h tend to 0, or the h approaches 0, can you see if the h, so we find the limit as h approaches 0 of Newton's quotient. And this here is the gradient of a tangent at a specific point. Now this expression here, we have a notation that we can use for it, and we refer that's it, and we read it as f prime x, f prime x, right? And that is known as the derivative of the function. And this is actually a definition, and this formula here is given to you on your information sheet. We also refer to f prime x, apart from the derivative, we also refer to it as the instantaneous rate of change. Now we're going to show you how we can determine derivatives using first principles. Let's continue. Let's look at the first example, how to determine the derivative using first principles. Example 1. Fx equal to 2x plus 3, determine the first derivative using first principles. What do we mean by first principles? That is, we must apply the definition, and this is the definition, and this definition is provided on the information sheet. So let's start off. We want to find the limit as h approaches 0. Let's put that division line over h. That's always over h. That's always h approaches 0. X plus h, so I must substitute x plus h in there. So that gives me 2x plus h plus 3. The x is replaced by x plus h. Subtract, and it's best here to enclose that in brackets. Now we expand by removing the brackets, and you notice the 2x and the negative 2x gives you a 0. 3 and negative 3 gives me a 0. And then I end with a simplified expression. However, h is not 0, so I'm allowed to cancel the h there. And that gives me limit of 2. This is the limit of a constant. So that it's constant, it just remains a constant. What is the constant? 2, irrespective of what h is. So that still remains 2. Let's see what did we obtain here. This is the first derivative, and what is the first derivative here? What's this derivative? This derivative here is the gradient of a tangent. And I want to know the gradient of a straight line. So what's the gradient of a straight line? The gradient of a straight line, there's it, it's given in the equation there. That 2 is the gradient. So the gradient here is 2. Therefore, I'm not surprised to get the answer 2 here. This is a constant value. The gradient of a constant is a horizontal line, and the gradient of a horizontal line is, that's right, is 0. So this one is just 2. So let's take another straight line. So what will the gradient of this straight line be? 5. Therefore, the first derivative is 5. What's the gradient of the straight line? 12. Therefore, it is 12. What's the gradient of the straight line? -6. So that's -6. What's the gradient of this straight line? That's right, there's a 1 there. The gradient is 1, right? So actually this part here, the constant part is always 0, right? The gradient of a constant is always equal to. Let's look at the second example. Fx is equal to x squared minus x plus 2. There we have a quadratic expression. We want to determine the first derivative using first principles. So we start with the definition. As you can see there's the definition. The definition is given on the information sheet. So let's write down limit. Draw a line straight through over h as h approaches 0. H always approaches 0. X plus h, so we must replace the x with the x plus h, and that x with the x plus h, that gives us that. Then we must subtract fx, or subtract. Let's enclose the fx in brackets. We then expand. We expand that, x plus 8, be careful with this. Expand that, and that's what we get after expanding. Some of the terms can neutralize each other, as you can see there. Negative x with a positive x, and a positive 2 with a negative 2. That gives us this expression here. Because h is not 0, it approaches 0, we can divide by h, and then we end up with that. This is now a polynomial. When you have a polynomial, the limit value of a polynomial is the function value. So we can just substitute h is equal to 0. We simplify that, and we get that expression. Just analyze it. You see, this is a constant, and the gradient of a constant would be a 0. This here is a negative x, so the gradient of that part there is -1. This one here is x squared, and its gradient is 2x. Right? Let's take something similar. I've got x squared plus 4x, so this one here, if we go through this process, what will that be? 2x plus 4. And this one, 2x plus 0. And this one, that's right, -2x plus 3. And the last one, -2x plus 0. So from this, we can already see we can find a short way of determining the derivative. Let's take another one. You're also required to find the derivative of a cube, x cubed. So let's use our definition. We then get the limit of h approaching 0, and there we have divide by h. X plus h, you replace the x with the x plus h, that gives us x plus h cubed minus x cubed. We now have to expand that. You can either multiply those brackets out, or you should know x plus h squared is x squared plus 2xh plus h squared. Similarly, x cubed is x cubed, x plus h cubed is x cubed plus 3x squared h plus 3xh squared plus h cubed, and then we subtract that. There are some terms that can cancel each other out, and I end up with that. H is not 0, so I can divide by h. That gives me this expression, which is a polynomial. Therefore, I can find the function value. So h becomes 0, that becomes 0, that becomes 0, and I end up with 3x squared. Now let's just look at this here. X cubed becomes 3x squared. So if I have x to the 5th using the same thing, that will become 5x4. X to the 7 will become 7x6. X to the 9 becomes 9x to the 8. X to the 11 becomes 11x to the 10. Right? So from this, we can already see we can find a rule for first principle, assist us in determining a rule for power. You should also be able to find the derivative of a rational function divided by 2 over x or 3 over x or -4 over x. And using first principles, that means we use our definition. We now need to substitute. So let's put x plus h in the x. So that will be 2 over x plus h. Subtract, so subtract 2 over x. What do we need to simplify fractions? That's correct. Find the lowest common denominator. The numerator will be 2 times x minus 2 times x plus h. Let's expand that. See there, we've expanded. Now instead of writing over h, I've now written that over h as times 1 over h. Right? It's much easier there. We can simplify. You can see the two x's neutralize each other. This h is not 0, so I can divide by that h, and that h. And I then end up with a simplified expression there. Because the denominator is not 0, I can substitute 0. And I end up with that. X times x is x squared. And there's the derivative of 2 over x. Let's just look at the given expression and the derivative. A positive 2 became a negative 2. Divide by x became divided by x squared. Let's see whether we can generalize here. Negative 5 over x will become positive 5 over x squared. 3 over x squared becomes negative 3 over x3. 4 becomes negative 4 over x4. Negative 2 becomes positive 2 over x, etc. Now we're going to show you some rules for differentiation, and then we're going to do an application of the. You only apply first principles if it's clearly stated that you have to apply first principles. Now there are different ways in which you can write differentiation, the derivative. Okay, so if I have y equal to fx, then the derivative can be given or written as, how do we pronounce that? F prime x. But instead of f prime x, I can also use the y, and I can say y prime. Or I can use the d dx notation, d dx of fx. Or d instead of fx, dy dx. Or mathematicians are trying to find the shortest way of writing, trying to economize. So d dx, we can just write down dx, right? So of fx, or we can write dx of y. It will also be necessary for us later to find the derivative of a derivative, right? That is the second derivative. Then, so I can have f double prime x, or the second derivative, or I can say y double prime, not y11 or f11. And we can similarly have d2 dx squared of fx, or we can say d2y dx squared. A little bit difficult on the tongue, but you'll get used to it. So these are the notations that we're going to use. Let's look at the rules that we're going to apply. The first rule is, if fx is a constant, in other words, you have a horizontal line, the gradient of a horizontal line is always equal to 0. Okay, so if I have fx equal to 20, the derivative is 0. Fx equal to 2000, the derivative is 0. Fx equal to pi, the derivative is 0. Let's take d dx of a power. When you have a power, as we've seen from our first principles, x to the 3 became 3x squared. So x to the n becomes nx to the n minus 1, where r is any real number. For example, x3 becomes 3x squared, right? X to the negative 1, you can even have negative exponents. So that becomes negative 1 times x, and the negative 1 must decrease by 1. So it becomes negative 2. You can even have fractions as fractional exponents. So that becomes half. X to the half subtract 1, and that's negative a half. Please be careful. If you're not sure, rather play it safe. Even if you embarrass yourself by subtracting 1, half subtract 1, you find the correct value there. So if I have x to the quarter, what would that become? That's right. A quarter x to the half subtract a quarter is negative 3/4. Be careful there. Now, quite often you have a power, but you also can have a coefficient. So k times the power will be k times, and then you just differentiate the power. Like 5x to the 3, there's the power, so it'd be 5 times 3x squared. like that, right? And 3 times 5 is 15. I hope you do this mentally. 5 times 3 is 15. 3 subtract 1 is 2. Then we can have, you see, these are only single terms. I can have multiple terms there. Derivative of, let's say, a sum or derivative of a difference is the derivative of the one term plus or minus the derivative of the second term. Let's illustrate that. Derivative there is a binomial. So I have derivative of 3x cubed plus the derivative of 4x to the half. And if I differentiate that, it becomes 9x squared, half times 4, 2x to the negative half. Let's now take some examples now. As you can see there, I have 1, 2, 3, 4, 5 terms. This one here, to find the derivative of the first term, that should be quite easy. Try that. 3 times 4 is 12x squared. Negative 4x to the 4, negative 4 subtract 1. Derivative of negative 5x is just negative 5. And the derivative of 8 is 0, right? So that one gives me this term, this one gives me this one, that one gives me this one, negative 5, x becomes negative 5. We can simplify that, and those are the terms that we obtain. Okay, now just look at this step here. You know, this is just to explain it to you, but you should be able to do this mentally. 3 times 4, you can go straight to the 12. 3 subtract 1, please don't embarrass yourself using a calculator to subtract 1. Negative 4x to the subtract 1, negative 5. Half times 4 is 2. Half subtract 1 is negative half. That's just negative 5, and that is 0. You don't have to write down the 0 there. Let's look at problem number 2. We need to have it in power form. You know, terms need to be in power form there. This is not in power form. So let's do the division first. So that's x5 divided by x2, 1 divided by x2. This radical, I need to write it in power form. That can be written as x to the 2/3. Still not ready? So x5 divided by x2 becomes x to the power 3. 1 over x squared becomes x to the negative 2. That's already in power form. Now we're ready to differentiate. So the derivative there is 3x squared negative 2x to the negative 3 plus 2/3 x to the negative 1/3. Let's take another example. Here we have an expression that's in power and that's in power, but we don't want any products here. So we need to expand that, and be careful how you expand. If we expand that, x times x is x squared. X to the 1 times x to the negative 1 gives me a 1. X to the negative 1 with x also gives me a 1. They're both negative. Negative times a negative is a positive. X to the negative 1 times x to the negative 1. Remember, we add the exponents. That's negative 2. Now we're ready to differentiate. Let's differentiate that. That's correct. 2x, negative 2x to the negative 3. Let's look at this example. You see there we've got a numerator and a denominator. We need to have it in power form. This is not ready to be differentiated. So let's try to rewrite that. That is a trinomial which can be factorized. And we notice the x minus 3 can cancel. I end up with that. Now we can factorize that. Derivative of this, it should be easy. You can see that's a straight line. So that's going to be a 1 plus 0. We don't write down the 0 there. Let's look at the last example now. Here we're going to show you how to do what is that? That's right, a second derivative. Let's find the first derivative of that, of x to the 4, that is 4x to the 3. And of ax squared, that's 2ax. Let's find the second derivative. That will be, that's correct, 12x, and the other one, plus 2a. Let's even try a third derivative, though we don't have it here. So that will be, that's correct, 24x to the 1, plus, and what will the derivative be of that? No, not 2a. This is a constant, right? Therefore, the derivative is 0. Now, you've been busy with differential calculus and derivatives at this stage. You must have been asking yourself, why are we learning this? I know most of you might not end up with fields of study or employment where you will be using mathematics and specifically calculus. Why differential calculus? Calculus is a branch of mathematics used to study any phenomena involving change. Like, we've got the change of our environment, the change in the infection rate, the change in the death rate, the change in the temperature, the change in my income, the change in my expenses, the change in time. There's so much involving change there. And then these situations can then be modeled, and then we can investigate the change. And as you said, we can have dimensions and time and force and many things there. Anything that involves change can be modeled, and then we can make some deductions from that. The purpose of studying calculus is simply to introduce your mind to the scientific method of analysis. Although we're going to have some specific applications of calculus, as we'll see in the next slide. The first one will be showing you applications of rates of change. Then we're going to show you how to find equations of tangents to curves. We did in analytical geometry equations of tangents to circles, but now with calculus you can find equations of tangents to any curve there. Then curve sketching. You did parabola and hyperbola and exponential. Calculus can assist us in sketching curves of functions. And then a very useful application of calculus is optimizing, finding the maximum or the minimum value, the maximum infection rate, the maximum expense, the minimum cost that you want to have there. Now, next, I'm going to provide you with an exercise worksheet as I do in all my videos, and I'm going to suggest that before you actually attempt this exercise worksheet, as always, go through the worked out examples in this video, but look at the question and you try to attempt the solution on your own. Do it with all the problems there, and if you get stuck, you just go back and see what error you made. And once you've done that, then I suggest you go to the exercise worksheet there. Now let's look at this exercise worksheet briefly. Here we have some questions on simplification of limits or determining limit values. Then here we have 5 problems on determining the derivative using first principles. And these are the 5 types of expressions you should be able to determine using first principles. A constant, which we haven't done, but I'd like to see how you do that on your own. A linear, a quadratic, and remember this quadratic doesn't have to be always 3 terms. A cubic, and we have a simple rational expression. One of these expressions are always assessed in an external or even an internal mathematics question paper on calculus. If you are busy writing a mathematics paper and you can't see any question on first principles, I suggest just raise your hand, call the invigilator, and advise the invigilator that you have the wrong question paper there. Let's look at the third type. Here are questions where you have to apply your rules. You do not use first principles here. Expand that, get it in power form, and then you differentiate. The same here, you simplify, get it in power form, right? There we just use different notations, d dx, d dx. Here, just a little bit of a different notation. Then the same here, you have to find that's right, the second derivative. But there's something I'd like to see how you're going to attempt this. I did not do an example like this because I'd like to see whether you can figure that out on your own there, right, from what we've done in this worksheet. Then there's another one, just with a different notation. There's another one. This one looks very familiar. And then the last one, just look at the last one. This part of the expression, that term, is already ready to be differentiated, but not that one, right? So you need to know what to do there. And here you have to find the derivative where x is -1. So you first find the derivative, and then you substitute. Okay. Thanks. I hope this will help you, and please practice this. And if you want the solutions to these 9 questions, if you subscribe to my channel and you comment there and you request the solutions, it will be forwarded to you. Thank you very much. Look forward to sharing you part 2 of calculus.